Okay, we've been working for the last couple of days inside of section 11.2 with curves, polygons, and symmetry. And we are to the point where we're going to talk about symmetry. So if you will turn there with me, the first thing we're going to talk about is what a line of symmetry is. A line of symmetry is a line which is its own image under a reflection over itself. You can think about it as a line that cuts the figure into two exactly equal pieces so that if you folded it, they would match. Okay? So if you take a look at the first one, does it have a line of symmetry? Here's some yeses and some nos. So it actually does not have a line of symmetry. If you were trying to cut it in half, say, vertically, and fold it, can you see what would happen? You can try it on your paper. It's thick enough to do it. Fold it down sort of like the middle of your page. And when you reflect it, one side is sort of indenting inward, the left-hand side, and the other side is sort of pushing itself outward along the top on the right-hand side.
Would a diagonal line not work?
That's a good question. Would a diagonal line not work? What happens if we were to try a diagonal line here? So let me draw that one in, the one you're suggesting. Sorry, my iPad's apparently cold because it was in the car. That's what it is. Okay, so let's see if we draw a diagonal line, what would happen? So you drew a diagonal line like this, what's going to happen? They're still not going to quite line up. Now, this particular shape, if we made sort of one consideration that said it was a rhombus instead of just a parallelogram and all the sides were equal, it would work. If it were a rhombus, it would work. But if it's just a parallelogram, that is that the top is longer than the side lengths, then it won't work. They won't line up when we try and fold them. So yeah, this one doesn't have any. How about the second one? Lines of symmetry. Where? Yeah, vertically. So like this. Close anyway. How about right? That's still not good. That's not too bad. Right there, something like that. Is that the only one? It has a horizontal one as well, like this. So there are two lines of symmetry on this one. So a rectangle is going to have two lines of symmetry. How about our square at the end? There are four. It has the same two that the rectangle had, so I'm not drawing them perfectly, but you have the right idea. What other two does it have? The diagonals, they work as well. And that's why the diagonals would have worked if we had a rhombus that we were talking about as well. Okay. We've got the basic idea. They're not drawn perfectly, but more or less. Okay. So square actually has four lines of symmetry. All right, so I'm going to let you guys take your hand at the next one. There are 6 shapes, and I would like for you to figure out how many lines of symmetry. So sketch them on there, you know, where you think they are, count them up, write down a number. So we're not going to take too long to do it, but figure out how many, and of course 0 is an option. We saw 0 before, but you can also have a lot of them. The square had 4 of them. So however many you have, write down that number. Okay, once you've written them all down, turn to a neighbor and just check to see that you guys have the same number of lines of symmetry for each picture. It's okay if you don't. See if you can figure out who is missing one or who has an extra one that it shouldn't be there or something like that. Okay, so confirm with someone nearby you, or a couple people maybe even, that what you have is matching up.
You're right. You know what I mean? Yeah, you're right. Because I'm showing pencil because I don't like making mistakes. That was a good guess.
Okay. Okay, let's take a look and see that we all now as a class have the same number for each of these. How many lines of symmetry did you get for part A? 6. What are they? I mean, can you describe the different types of symmetry lines there are?
Every, corner and side.
Okay, in the corners, those actually have a name. Do you remember what those names are? Does anyone remember? The corners are called vertex, and when we draw a line through them, what do we call that? No. Starts with a D. Close. Diagonal. Yeah, diagonal. So those are diagonals right there. Okay, there's a diagonal that matches non-adjacent vertices. And these are obviously very specific non-adjacent vertices because they're the ones that are directly opposite each other. And there's 3 of these, right? And then what was the other type that you said, Abby?
Like the middle of each side.
Okay, so like this.
Yeah.
At least if I drew it well. Okay, and that would be 6 of them, yeah? So there are 6 here. How about the letter A? How many does it have? 1. That's right, just 1 right there. How about it looks like a track field to me. It's like a track. Okay, how about the track? 2. So we have a vertical one and we have a horizontal one, right? So there are 2. How about this letter Z? Z0. Yeah, there's nothing there that will work for us. How about our arrow sign? 1. Where is it? In the corner. Very good, Hannah. So like this. I think that'll do it. So there's 1. And the 4-way arrow. Apparently you can go any direction you want if you encounter this arrow. 4. So can you tell me where they are, Alyssa?
Up and down. Horizontal. And then between each.
So like this. Yeah. So we have 4 on this one. Okay, so lots of different options for how a figure can look and how many lines of symmetry we can end up having. So that's one type of symmetry, line symmetry. Second type of symmetry is called turn symmetry. Now, turn symmetry is also sometimes called rotational symmetry. So I'm probably going to say rotational symmetry because most of the resources that I've used have used that phrase, but they mean the same thing. It means you're turning, you're rotating something. A figure which is turned by some angle less than 360 degrees around a single point, and the single point is called the turn center, and it causes it to match up with the original figure. So if you rotate something 360 degrees, what happens? It's exactly where it was before, okay? So every figure has a 360 degree turn rotation symmetry. That's really not a helpful piece of information, okay? So that's why we're excluding that possibility. We're only looking at the possibilities that are less than 360. And again, if it were more than 360, it would match up to something that's less than 360, so we don't really have to worry about the more than 360 case either. All right, so taking a look at these figures, the first shape right there, you know that shape, you see it places, right? Recycle symbol, yes. Does it have a rotation symmetry? Can I turn it less than 360 degrees and it will land back on top of itself? Yes. And so this one would have a rotational symmetry, and I'll talk in a second here. Actually, it's on the next slide. The recycle logo coincides with itself after a turn of 120 degrees about its center. We say that the logo has a 120 degree turn symmetry. We could actually rotate it by another, this should say 120 degrees. Like after the first 120, we rotated another 120, and we get a 240 degree rotation symmetry. Now you might be looking at that and say, well, where did the 120 and the 240 come from? Well, I mean, 240 came from adding 120 to itself, so where did the 120 come from? Well, it actually came from taking 360 degrees, because that's the full rotation all the way around that puts it exactly right back on top of itself all the time, and dividing it, in this case, by 3. Any idea why dividing it by 3 makes sense on this particular shape? Yeah, this is almost like a triangle, right? I've got these sort of three matching images. This piece looks exactly like this piece, looks exactly like this piece. There's three matching pieces here, and that's why I'm dividing by 3. So if I took 360 and divided by 3, that's where the 120 comes from. Now take a look at the other one, the middle one right here. It looks like a tire, right? How many matching pieces do you see in this particular shape? There are 6. So if I wanted to know the rotation symmetries, and there's more than one, of this, what would the first rotation symmetry be if I used this sort of an idea? 360 divided by 6, and I would get 60 degrees. So the car tire has a 60-degree turn symmetry. So, I'm sorry, I didn't flip to this slide already. To find the amount of turn symmetries, divide 360 by the number of similar shapes or possible rotations. This would be 60 degrees. But if there's a 60-degree rotation here, what else is there? 120 and 180 and so forth. 240 and 300. 300 is the next one. We just add 60 to it multiple times, and we'd have all of those turn symmetries that would work. All right, I'd like for you to do the same thing with these 3 shapes. The first 2 are very familiar shapes as well. I believe they're both logos from cars, correct? Yeah. So find the rotation symmetry, the rotational symmetry for the figures. And we'll just write the first one down. We're not going to write down all 6 of them. Like we could have written down 60, 120, 180, like that on the last one, right? We'll just write down the first one, okay? So what would the smallest rotation symmetry be for each of the figures? So write down what you get for each of the 3, and then we'll compare notes. All right, how many similar figures, so to speak, do you have in the first one? What did you divide by? 2. So you ended up with a 180-degree turn symmetry. What about the second one? There's 5, right? 5 similar shapes, 5 triangles actually. And so if I take 360 and divide by 5, I get 72, so that's a fun number. And then the last one had how many similar shapes? 6, and I divided that one and I get 60, much like the car tire I had before. Whoops. Did we actually talk about, hang on. We didn't actually talk about that last one. What does this last one have over here? Yeah, it's 90. How'd you get 90, Amy?
There's 4.
Yeah, 4 similar shapes, so 360 divided by 4. This one had 90-degree turn symmetry. Okay, there is a note on this page. I don't think it's actually in your notes, or is it? It's not. I didn't think so. I was looking at it. It's not in mine, but a figure can have line symmetry, rotational symmetry, both or neither. So they're not mutually exclusive things. So if you take a look at the first picture on this particular slide, this one, does it have line symmetry? It actually doesn't. There's no line that I can draw that will flip it over on itself and actually match up. How about the second image? Yes, it has several line symmetries, in fact. Do you know how many? Some of you are drawing in midair. Here's one of them.
4.
Here's 2 of them. Here's 3 of them. Hang on, did I get it drawn right? 4 of them. 5. I think there's 5. Did I get them all in there right? Through every sort of corner and opposite side. There's 5 symmetries, line symmetries on that one. What about the next one? How many are there on that one? I think it's just 6. I think it's just 6. The even ones usually end up being themselves, and the odd are, did I say that right? So, yeah, see, so here's 1. We'll draw them in. 2 and 3, like that. So they sort of duplicate because there you get both corners at once. And then here's the other 3, 4, 5, and 6. It's much like the original hexagon that we had on the previous slide. Yeah, so there's actually 6 of them. So on the first one we had turn symmetry but no rotation, or yeah, turn symmetry but no reflection symmetry or no line symmetry. But on the others we ended up having both. There's one more type of symmetry, and it's called point symmetry. Point symmetry is just a specific kind of turn symmetry. It's a figure that has 180-degree rotational symmetry about the turn center. So it's really not a different type of symmetry. It's just a very special name for one of the types we already had. Okay, 180-degree rotational symmetry or turn symmetry is called point symmetry. The turn center becomes the midpoint of the line segment through any point in its image. So let's take a look at the ones that we have and decide if they in fact have turn symmetry. The first one, can you see where the whether it has turn symmetry or not? Yeah, it does. And the turn center is where? Yeah, right here in the middle. And it talked about connecting every point in its image. So for instance, if you take this point and you reflect it 180 degrees, it'll be right here. That would be its image after the rotation. And if you were to connect them with a line like this, then the turn center is the midpoint of that line segment. That's what it's referring to. And you can do every point in its image and it will create these segments where the turn center is the center of that segment. How about the second one? This green oval shape. Yeah, it would be the center of the oval, right? And again, every point, so say we used this point, its image would end up over here, and sure enough, if you connected these to the line segment, it would be in the center of the line segment. The last 3 are actually, or the next 2 are actually marked. The center is actually O, right? If I used that as my point center and I turned it, I would have 180-degree rotation. And the same thing here for the center H now, for the H, which is the center O. This one's a really interesting shape because all the shapes that I've done so far, the lines I drew actually connected part of the shape to itself. And you can see that this line, it doesn't, right? It's not actually part of our shape. But it still creates a segment, and the turn center is the midpoint of that segment, even though the segment itself is not on the shape. And the last one does the same thing. We've got this very interesting shape. Looks like it should be on like a banister or something like that. And every point is connected. So this point they used as an example, its image is this point, and its line segment that connects them looks like this, and the turn center is right there in the middle, which is the midpoint of that segment. So that's what happens on any of our point symmetries. The turn center is in the middle of the segments connecting them. Circles are very interesting, or maybe not so interesting depending on your perspective. So if you take a circle as a consideration, a circle will have infinitely many lines of symmetry, each of them passing through the center of the circle. So if I pass through the center of the circle, what is that line called? Diameter, exactly. This would be a diameter. So every diameter of my circle, and there are infinitely many diameters, would be a line of symmetry. All of the circle's lines of symmetry intersect at the circle's center, obviously. A circle also has infinitely many turn symmetries, each of which uses the center of the circle as the turn center. And it has point symmetry, the center of the circle. So if you think about this particular shape and you turned it 1 degree, or you turned it 346 degrees, or you turned it 123 degrees, they're all going to work and land the circle right back on itself, right?